Let me introduce Dr. Enzo Mangano. Dr. Enzo is a senior lecturer in chemical engineering at the University of Edinburgh, expert in nanoporous materials for gas absorption. He developed a system to measure equilibrium and kinetics at high pressure. His work contributed to the CH4 reference isotherm in an international project by NIST. He also co-authored the IUPAC report on gas transport in nanoporous material and received the 2016 Italy Made Me Award from Italian Embassy. The presentation title is Determining the Absorption Properties of Novel Nanoporous Material for the Evaluation of Water Absorption Performance. Please, Dr. Enzo. Thank you.
Can you all see it?
Yes, perfect.
Perfect. All right, so welcome everyone. Sorry for joining late the meeting. I've been teaching up to half an hour ago, so it's been a little bit complicated. So my presentation is about a technique where we use in our lab to measure water absorption. We are able to measure kinetics and absorption equilibrium for water vapors. Professor Brandani and myself will lead the absorption group here at the University of Edinburgh. We have quite a number of techniques, and we cover all the sample masses from a few milligrams, which is the zero-line column, which is the focus of this presentation. Then we go up gradually in mass up to kilogram scale, so full-size columns. And obviously, for each of these equipment, we also have tools for simulations or model simulation for milligram up to kilogram scales. Our lab is equipped with, as I said, like the zero-line column, but also balances, high-pressure balances, low-pressure balances, like the Aquadyne for water vapor, and volumetric systems, which are differential volumetric systems, which we designed going from low pressure to high pressure. Okay, so the talk is obviously focused on our work on water absorption, and the focus is on water harvesting. Obviously, it affects the scarcity of water affects millions of people around the globe, and obviously one of the solutions that researchers found is to harvest water directly from atmosphere. One of the possibilities, obviously, that concerns our field of research is using absorption-based harvesters that are essentially designed in the simplified schematics, like in this slide here. So essentially absorb water at high humidity during the night, and then you use the energy that comes from the sun to essentially heat up the solid and absorb the water from the system, and then eventually condense it and get the water out of it. So obviously the key issue here is to find the right material to do that. And because we work in absorption, we work with nanoporous materials. So we are looking for materials that have certain properties that are ideal for this process. So we want something that can be regenerated at low temperature, because obviously the impact of the energy will be lower, with as much as high absorption of water, fast kinetics probably, and that can operate at low relative humidity, because we are capturing water from the atmosphere. So obviously there are a number of choices of materials available, and obviously we work with chemists that can design materials that are the most suitable for this scope. So how do we normally measure water absorption? So classical methods are, you can saturate your sample with water, you get like a single point, you get the mass before and after, you get the amount absorbed. Or you can use balances that are very accurate, and you can do like repeated points to get the isotherm, or volumetric systems. Again, very accurate system, all commercial, but also very time consuming. In our lab, we use a technique which is called the zero-line column. The zero-line column is essentially the limit of a breakthrough experiment going into a very small sample masses. We are working with less than 1 milligram for our experiment, and what you get is essentially the absorption curve for the sample. and we analyze the system, assuming that it's essentially a CSTR, because in the limit of zero length is essentially a CSTR. So how the experiment works, you saturate your sample with your adsorbate, that can be water in this case, and then you desorb. We normally look at the desorption curve, but for water experiment, we look also at the adsorption curve. We integrate the signal, and essentially applying the mass balance, we obtain the overall amount adsorbed and the isotherms. Okay, so what's the advantage of doing it with this technique compared to other techniques? If you look at the other breakthrough systems, for example, CO2 in 13x, the issue is that even for small sample masses, so say in this case, this is just 23 grams, you have a temperature change within the columns of almost 50 Kelvin. Our system, instead, working with very small amount of sample, allows to run the system practically in isothermal conditions, which is very important the moment you want to measure kinetics accurately on these small quantities. Okay, so in the case of water, what we do is that we obviously work outside the linear range of the isotherm. We look at the entire profile of the isotherm from 0 to practically saturation. We work at very low flow rates and very small amount adsorbed. And obviously, because the concentration varies a lot, we also correct for the flow rates. The system looks like this. So we have essentially mass flow controller where we flow the gases, we saturate with water. We have a bubbler that allows us to saturate, to change essentially the relative humidity of the water. And we flow the system through our zero-length column system. And we use as detector a mass spec and a humidity probe that gives us both the concentration profile and the actual concentration running outside the column. Okay, so the moment we run the system under equilibrium control, what we have is that if you run the system at enough low flow rate, the system is essentially very fast, i.e. is under equilibrium control, which means that every point of the curve would be an equilibrium point. You can verify that by changing the flow rate. If they overlap in an FT plot, so flow rate times the time, it means that they are in equilibrium control. So each point inside is an equilibrium point, which means that if you integrate it, essentially you get the shape of the isotherm. So for our experiment, this is a typical profile of the raw data for our experiment. You have the adsorption branch in red, and the green would be the desorption branch. So you saturate, you reach a plateau, then you go to a new plateau, and then you desorb. You integrate the system for both the adsorption and the desorption, and you obtain essentially the isotherm, both for the adsorption branch and the desorption branch. You can change the mass, the sample mass, and verify that the system essentially is reproducible. And you can also run scanning curves. So you can purposely not saturate the system and actually run the adsorption desorption in scanning mode. We have verified our system also with commercial balances, and essentially we get the same amount of data, the same profiles, but with more than 10,000 points, and in just a matter of 24 hours, maximum 2 days, compared to 9 days that would be our commercial gravimetric system that we use for double checking essentially our results. Obviously, the real other limit is that if you want to measure kinetics, what you want is that you want to push your system into the kinetic regime to measure the actual mass transfer of the water inside the sample. So this system at the moment, the one I'm showing here, is water on SABA 15. You increase the flow rate like you see in the plot on the right, and you push the limit towards the kinetic control, and now the curves do not overlap anymore. So now we are in the conditions where you can actually measure the kinetics. So if you have like no crossing, so no overlapping in the FT plot, you are essentially in kinetic control. For the part that this second part of the talk that will cover essentially the kinetic regime, this is a work that we published quite recently in 2022, and is based on the mass transfer coefficient of silica gel for water in silica gel using the zero-length column. Okay, so in this case, I'll give a small introduction about what type of mass transport we expect. So in the case of a commercial material that has macro, meso, and micropores, in the case of macropore diffusion, you have a few controlling mechanisms that can affect essentially the total pore diffusivity. One is the molecular diffusion, which depends on the carrier gas. The other one is the Knudsen diffusion as you go into the mesopores and smaller pores. Then you have also viscous, and eventually, in some cases, you can have also surface diffusion. Okay, so in surface diffusion, you also have the contribution of the early law constants of the slope of the isotherm in the K that you see in the equation here. In the case of mesopores, normally, which is relevant for this case, in the case of a sample that is dominated by mesopores, Knudsen diffusion would be the mechanism that would be dominating in this case. You can write the mass balance for the macropores and essentially get the effective macropore diffusivity. And you will see that the main dependency is the slope of the isotherm. So if you look into the equation at the bottom, you will find the void fraction, the total pore diffusivity, dP, and then at the bottom, in the denominator, you find dF of dC, which is essentially the local slope of the isotherm. So this means that you need a very accurate isotherm measurements to actually determine accurately the mass transport coefficient of water inside the sample. So our system, we only loaded a fragment of a silica gel bead using just 4.3 milligram of sample. We also ran a mercury intrusion and extrusion pore size distribution, which is the plot in the slide here. And as you can see, the system has practically no macropores, and it's all mesopores, okay? So this means that any result of the mass transport should be independent of the carrier gas, because now we don't have any molecular diffusion going into this system. So it should be dominated essentially by Knudsen and potentially surface diffusion. So starting from that, we can write now the mass balance for our system. So here we have the mass balance of the system. So the accumulation in the gas phase, the accumulation in the solid phase, and the flow rates coming in and coming out. We can define also a mass transport coefficient, which is essentially Ka, where A is the surface to volume ratio. And if we combine the two, essentially we obtain an expression where essentially we have an equilibrium is essentially our isotherm, and hence we need a very accurate measurement of the equilibrium to get the isotherm. All the rest is essentially all given in our experiment. So if you combine the two equations, you will see that the Ka essentially depends only on the flow rate, which we know, the concentration coming in and out that we measure, the flow rate, the volume of the fluid, which is essentially measured in the blank of our experiment. So we can essentially calculate Ka by simply analyzing the singlet that we get out from our experiment. So we did this, we measured the isotherm using our zero-length column system in flow. We obtained more than 10,000 points. We measured the isotherm at 25 degrees, both in adsorption and dissolution. And here you see plots overlapping at different flow rates, meaning that the system doesn't depend on flow rate as we expect for an equilibrium measurement. You see the adsorption and the dissolution branch here. And this one comes from the integral of the breakthrough experiment of the system. So because we have so many points, essentially we don't need a model based on the equation I just showed. We simply interpolate, because we have so many points, we don't need a isotherm model. We can simply interpolate the data that we get and use this one directly to calculate the mass transfer coefficient. So we did experiments at 3 different temperatures, 25, 10, and 40 degrees. And 40 degrees, for example, if you notice, is practically a scanning curve because you don't reach saturation. So you do the adsorption and the desorption by partially saturating the system. These are the measured mass transfer coefficient. In black is the desorption branch, and in empty points, and so no filled points, is the adsorption branch. So what you see here is that obviously we are doing this at different flow rates. So the flow rates goes higher as you go from the plot on the left to the right. And for each of the flow rates, what you can see is that the mass transfer coefficient at the desorption is practically constant, while the one in the adsorption shows a high value, a low concentration, then it shows a minimum, and then it goes up again. And the minimum corresponds to where you have the inflection of the isotherms, i.e., where it becomes very steep in the adsorbed in the uptake. And essentially what you get is that as you go up in flow rate, it becomes into a completely kinetically regime system, so it becomes independent on the flow rate. We extract this value, and then we can actually use it in our model to predict. So these one are the now the profiles, the experimental profile normalized in concentration, so C over the bubble concentration, bubble point concentration. You have the adsorption branch on the left and the desorption branch on the right. You can see that, as you will see in the plot before, the mass transfer coefficient is practically constant in the desorption, so allows you with a single parameter to match very well the desorption, while you have a very good match, but not as good as the desorption for the adsorption. This is assuming a single parameter, which is 0.0049 for the case at 25 degrees. Okay, so it means that obviously this methodology allows you to get with a single parameter both the adsorption and the desorption. The adsorption will require more attention in terms of a more complex model for what regards the mass transport, but the desorption is definitely satisfactory. We do that at different temperatures. This way we can actually obtain the activation energy of the process of diffusion of the transport process, and the activation energy comes out at a value of 19 kilojoules per mole. You can compare this one with the latent heat, and it comes out roughly half of it. This means that there is not only the Knudsen resistance to the system, but also a contribution from the surface diffusion. Because if you remember from the equation that defined the mass transport in the macropores, the surface diffusion has a contribution with the slope of the isotherm. So there is a dependency of the isotherm with the temperature, which is included in that term. Now the final check is obviously you are in the regime of macro mesoporosity, so you want to check if your kinetics changes with the change of the carrier. And what you will see here is that we did all the tests using nitrogen as a carrier, so it was a mixture of nitrogen and water. And for the check, we changed the carrier to helium. Now, in a normal macropore system, this will indicate that the system is controlled by macropores, because changing the carrier will change the molecular diffusion. But because the system we measured had essentially no macroporosity, but only mesoporosity, molecular diffusion does not play a role in this case. So what we see here, the fact that they do not overlap, indicates that potentially the system is not under isothermal conditions. So what we did then was essentially to look at a very simplified calculations. So for the flow rate and the size of the particle we were using, we obtained a Knudsen number of 5 to extract essentially the heat transfer coefficient. And we modeled, essentially we calculated the delta T with the time obtained for the flow rate that we were using. And what we see here is that when we use nitrogen as a carrier, because of the difference in the heat capacity of the nitrogen, you get a big drop in temperature as you start desorbing. with about 14 degrees difference at the first 200 seconds, and then it levels off and goes into an isothermal regime, while helium has only a drop of 2 degrees. So helium is practically under isothermal conditions, while nitrogen is clearly non-isothermal. So there is a contribution from the non-isothermality into the value of the mass transfer coefficient that we extracted from this experiment. So this one essentially tells you that even in a system with very small amount of sample, in our case was only 4 milligrams, a system with water, which is essentially with a high heat of absorption, is always prone to non-isothermality. Hence, we have to take into account in case, and we have to have ways to actually check if our system is isothermal or not, especially if we want to extract the diffusion parameters for the system. This one essentially concludes my talk. So what the key point to get from our experience in measuring water is that water absorption, especially measuring the water kinetics, is very complex. You need very accurate isotherm data, and because there is a strong concentration dependency of the diffusivity with the shape of the isotherm. We developed this system, which is the zero-line column, adapted from gas absorption to vapor absorption, to actually use a system that allows us to have a lot of definition in terms of number of points. It allows systems, so measurements, to be done in a fraction of the time compared to gravimetric and volumetric systems that are essentially available commercially. It can be done with very small amount of samples, so it's ideal for chemists that, for example, produce only very small amount of samples. And obviously, we can use that one by playing with the flow rates and the temperatures. We can explore the system under equilibrium and kinetic regime, because for the kinetic regime, you also need a very accurate isotherm. And obviously, even with our system, we notice that there are conditions where isothermality is not always guaranteed. So you actually need to have way to check and include in your models. And then obviously, we also detected the presence of surface diffusion in the mesopause for our water in silica gel system. With this one, I conclude my talk, and I welcome questions from the audience. Thank you very much.
Perfect, Dr. Enzo. Perfect. Really, I really appreciate. Thank you very much. It is very noble. Okay. Any question? You can raise your hand or you can write out in chat. Daniel mentioned, thank you, Dr. Enzo. Have you published these findings where we can read more of this?
Yes, so these one are all, most of these are all published. So we have, so the findings of the two core part of this has been published. So one paper is presented in halfway through the presentation, and is from 2002 in 2022 in energy, and the other one is a little bit from before. We have currently two projects running on water absorption, one on water harvesting and the other one on water absorption. We are looking at the entire isotherm, and the other one is only looking at the absorption from atmospheric conditions. And the two PhD students should be connected here to be present at this presentation as well.
Any other question? You can just simply raise your hand or write out in chat. In meanwhile, I would like to ask a question.
Yeah.
Can you elaborate how the ZLC ability to measure mass transport kinetic enhance the understanding of material performance in low humidity condition?
Right. So essentially, in low humidity conditions, actually what you have is that it kind of simplifies the issue, because you don't have to go all the way up into the nonlinearity region, And the zero economy is being invented, and we use it normally in very low concentration. So actually working in harvesting in atmospheric absorption of water is a little bit easier. So you tend not to get to the branch where you actually have the adsorption and desorption hysteresis. So you work in the bit of the isotherm, which is the low bit, where adsorption and desorption coincide. And in these terms, you simply lower the concentration of the relative humidity at the inlet, and you work in that region there. But the analysis then is practically the same. You remove the complication in some cases to have the hysteresis, so that the branch of the adsorption and the desorption are not the same.
Perfect. Any question? You can just simply raise your hand or write out in chat. If not question, we can try again with Dr. Yong. Any question? Yes, we have one question. Let me unmute you. Yes, please. Hunter?
I think it's muted.
Yes.
Oh, yeah,
we can hear you.
Thanks. So it was interesting to understand better how the adsorption curve doesn't follow the isotherm. And that sounds like a frustrating thing for characterization. But effectively, that it follows a different path in absorption than desorption. Is that the kinetics involved in that? Is it possible to implement to a practical use, or is it always working against applications that we might have in mind? If that makes sense.
I don't know what you mean with your question, sorry.
Sorry. So I'm imagining the uptake in the release phases for a particular absorbed material for water harvesting. It's convenient to have those curves it might be useful to have those curves not the same as each other.
Yes.
But I guess you get hysteresis, which always acts against you, or is there some way of tuning kinetics for a useful purpose if it's understood better?
Well, if it's understood better, you can actually run your cycle in a way. So essentially, if you understand the kinetics of the system, so intrinsic fundamental kinetic of the system, then you can tune your cycle to be, for example, allow longer time in adsorption than desorption, or vice versa, depending on how, because you see the dependency of the diffusivity of the transport with the concentration is the local slope of the isotherm. Okay, so you may have that the desorption branch is much steeper than the adsorption bit, hence going very slow compared to the adsorption, for example. So you may have the desorption bit is going to take a lot longer. Hopefully, the material that you select for harvesting works at a region below in terms of relative humidity from the hysteresis, so you shouldn't experience that in principle. But obviously, the effort on understanding the kinetics on such complex system is that obviously the moment you start having cycles in adsorption and desorption, then you want to know if it's taking you 3 times the time in desorption than in adsorption, and how you can mitigate for that. Remember, you can also play with the temperatures. So obviously, the moment you change the temperature, your isotherm changes slope as well. So if you regenerate by using the temperature, you can play with the temperature to accelerate the process.
I see. So materials are usually shown to be useful based on their isotherms, but if the kinetics was a different way of tuning their performance, I didn't know if that was something that was explored very much. Well,
in these cases, for most of the material, these are macropore diffusion control. So a lot of the dependency of the diffusivity depends on the local slope of the isotherm. You may have materials that are more with pores closer to the size of the molecule of water. In this case, you have a configurational type of restriction, and there you can tune the pores to make it faster. But in every adsorption process, what you want is the fast process. You want to finish want to have a fast process so that your cycle is fast and increases the productivity. And by increasing the productivity, your unit is smaller.
Thank you.
Thanks. Let me take one question from chat. Is it possible that the material is connected by water and leaked out, similar to moth? I mean the hydrogen bonding with water and extract by hydrogen of water.
I'm not sure I understand the question.
Yes, likewise. And so we can take another question. Do you see absorption-based atmospheric water technology becoming commercially available?
Well, surely has there is no from what I know there are prototypes. Haven't seen like large scale units on this. A lot depends on the material selection. Because obviously we are processing a lot of gas, a lot of air to extract water. So there is an effort at the moment to work into optimizing the material as well. So making monoliths or structural material like the ones that we use in the in the catalytic converter of a car. Okay, stuff that allows a lot of flow through and very efficient heat transfer changes. But obviously there is a case for that, because the advantage of the absorption is that in terms of the energy required, actually is quite efficient, because you cool down and absorb, you heat up and absorb, and you can use the cycle of essentially the day and night to help with that. So potentially as a future. And there is a lot of interest at the moment from industry and chemists to actually develop material for that.
Thank you, perfect. Any question? If not, we can go to the next section.
Thank you very much.
Thank you, Dr. Enzo. I really appreciate and enjoy. Now it's the time to hear from Dr. Yong. Dr. Jin is a postdoctoral fellow at Water Desalination and Reuse Center at King Abdullah University of Science and Technology Coast in Saudi Arabia. He earned his PhD in Environmental Science and Engineering from Coast in 2019. His research focuses on designing materials and devices to address phase change phenomena in areas like condensation, heat transfer, and desalination using principle of thermodynamic and transport theory. Can you please share your screen?
I'm trying, but I don't think what happened.
Let me check your... Yes, right now we can see your...
You can see it well?
Yes, we can see your screen.
Sorry for the problems, and thank you for the invitation and introduction. So I'm happy to present my recent work about storing water vapor during high humidity for freshwater production in low humidity periods. As we may have the consensus that water harvesting at low humidity level is more energy intensive and might be more expensive. So the question is, can we develop a strategy to avoid the water production at low humidities? We can see from this figure on the left that in a desert location, in some months, the humidity level is high, while in others, the humidity level is low. So we are trying to develop a strategy to use more solvent materials to absorb water vapor during these high humidity periods and use the stored water vapor to produce fresh water during these low humidity periods. For example, we can use like liquid solvents to absorb water vapor during high humidity times and produce dilute solutions and use that dilute solutions during the low humidity times. This strategy we want to address is kind of feasible or not. This is a question. Another question is we have like, as I mentioned, we use liquid solvent other than the solid solvents, because the solid solvents like moths, they had a problem with compatible with the fluctuating humidity pattern. For example, this moth gets saturated at a humidity level of around 10%. This means that if the humidity increased to more than 10, like 20 or 30, the absorbed water will not become significantly increased. If the humidity level is lower than 10%, then the absorbed water will become negligible. So this stepwise absorption isomer is not compatible with the fluctuating humidity pattern. So the humidity pattern is fluctuating, and we are developing this strategy. Is this strategy feasible economically? So this is a key question we want to address in the following content. So before we answer the question, we built an atmospheric water harvesting system, which consists of two devices. One is the production device, the other is the absorption device. The production device is as a similar configuration with like membrane desalination process. In the production device, hot feed and coolant flow in opposite directions. Both of the feed and coolant are hygroscopic solutions, such as like a calcium chloride solution, lithium chloride solution. Well, when the hot feed flows in the channel, water vapor evaporates from the hot feed and condenses on the coolant side. Therefore, the coolant is heated by recovering the latent heat and other forms of heat from the hot feed, and then the coolant will be further heated and enter the hot feed channel. In the absorption device, firstly, the concentrated hot feed is cooled by a chiller to the ambient temperature, and then the cooled concentrated feed channel feed solution is supplied to the absorption device, and water vapor can be absorbed in this absorption device to produce dilute solution as a coolant, which enters the coolant channel in the production device. As you can see, we have like 3 levels of humidity. One is the ambient one. We have it in the atmosphere, and the other one is the production level, and the third one is the absorption humidity level. The production humidity level and absorption humidity level are equivalent to the concentration of the hygroscopic solution. So and also ambient humidity level is always higher than the production humidity level and absorption humidity level, because the hygroscopic solution is unlikely to in absolute equilibrium with the ambient condition. So we can determine the production humidity level in the device. For example, if the production device the humidity level is close to the ambient humidity level, then the production rate, water production rate, will be higher. but the driving force in the absorption device will be small. So in otherwise, if the production humidity level is low, far from the ambient humidity level, then the water production rate will be decreased, but the driving force in the absorption device will be higher. So this is a balance between these two parameters. And then we established a techno-economic model to simulate the atmospheric water harvesting system. With this model, we can see from this figure that the cost, the levelized cost of the water production at higher humidity is lower. So this means that we have much room to play with the strategy we just proposed. Let's dig into more details about the model, the cost model. Generally, the model the water production cost is composed two components. One is the capital cost, the other is operational cost, daily operation cost. The capital cost includes like the module, the memory modules, investment, the heaters, the heat exchangers, pumps, and the chemicals used, and the water storage tanks. So these are capital investment. Operational cost includes the energy consumption, such as electricity price cost. And also, you have to replace these membrane modules from time to time. So this also costs money. So these price listed in the table are obtained from the online vendors, and some of them also obtained from literatures. So the calculation of capital cost and the operational cost is listed here. Generally, capital cost is calculated by the total capital investment times the investment rate factor and times the interest rate. So the operational cost involves parameters such as pressure drops and the energy input in the production device, and also the energy input into the absorption device. These parameters can be calculated by a fluid dynamic model coupled with heat and mass transfer. These parameters like flow rate, hot feed inlet enthalpy, coolant outlet enthalpy, hot feed outlet enthalpy, and pressure drops within the system, and vapor fluxes. All these parameters and can all be calculated with the model and be supplied into these calculations to get the operational cost. So the final product is the levelized cost, which is equal to capital cost plus operational cost divided by the water production rate. And then with this techno-economic model, we first calculated the minimum levelized cost, assuming that we have a constant relative humidity and temperature. Here are the results. From these figures, we have two pieces of information to deliver. One is you can always find a minimum value for this function, for this minimum levelized function as a function of temperature. You can always find a minimum value for different relative humidity. The other information is this function is a convex function. So this means the values between these two ends is always smaller than the average of these two ends. So this is quite important information I will mention later. So let's move on. Oh, what's the problem? Anyway, just discuss this equation. This is the most important equation here. So the average, now we start to deal with the fluctuating humidity pattern. Just now we calculate the levelized cost for a constant relative humidity and temperature. Now we start to deal with a fluctuating pattern. So we do it on a daily basis. We do the operation of water harvesting on a daily basis. So within one day, you can have a water production cost like CI, and this is equal to levelized cost times the water production, water produced, WI. So if you want to get the minimum of this average levelized cost for a fluctuating pattern, then each value of these levelized cost for each day should be minimized, which is presented here. But you notice we have a lot of humidity data in a fluctuating humidity pattern. So this would be a very large number of work you have to do. You have to calculate a large number of these levelized costs for each humidity data. So we figure out a more easy way to calculate the range of the average levelized cost by normalizing this fluctuating pattern into a constant pattern. So you can imagine there's a solution with a concentration which is equivalent to a constant relative humidity and at different temperatures. Then you can calculate the flux from this fluctuating pattern to this constant pattern. If you sum up the flux, then the flux is, if the summation of the flux is 0, then you can assume that this fluctuating pattern is equivalent to the constant pattern. So now you can just use a constant pattern to calculate the range of this average levelized cost. For example, if the normalized pattern is equal to like 80% of the relative humidity, and then you can get a range like this minimum is a low bound of the average levelized cost for a fluctuating pattern, and this average between these two ends will be the upper bound of the fluctuating levelized cost pattern. So with this model, with this methodology presented above, we start to evaluate the feasibility of storing water at high humidities. The first mode we may conduct storing water is that we can store water at nighttime, because at nighttime the relative humidity level is always higher than in the daytime. For example, here at nighttime the humidity level is higher, so we can do the water absorption at night with more hygroscopic solution. So this we can do like absorption for like 12 hours at night, or 8 hours at night, or 4 hours, or 1 hour. The difference is if you do like 1 hour's absorption, then the normalized humidity level might be high, but you have to use much more hygroscopic solution for the absorption, and you might need more absorption devices for this process. So this figure shows the normalized humidity level for different absorption time. So for this different absorption time, we calculated the range for the average levelized cost. So if you do like 20 hours continuous absorption, so the low bound of the cost is like 210 US dollars for 1 cubic meter. But if you do like 8 hours absorption at night, then you can save as much as like $40 for this process. And this is the first mode. You can do it at night on a daily basis. So the second mode is to store the vapor during the high humidity times within 1 year. For example, you can do water absorption above the humidity level of 90% and within 1 year. But you have to notice that the periods when the relative humidity level is higher than 90% is short. So this means that you have to use like more hygroscopic solutions and more tanks, more absorption devices to produce more like dilute solutions for use during the low humidity level periods. This figure shows us the absorption hours at different humidity levels. Like if the humidity level is, you conduct the absorption above 20%, then you have much more times for the absorption. But the normalized relative humidity is low, so there should be a balance between these two. But overall, we use the techno-economic model. We calculate the price for the average levelized cost. We can find that in some cases, like here, if you do absorption over 80%, you can have a maximum of the levelized cost of like less than 180 US dollars, which is also lower when, as shown here, like $210. So this means that this mode is also feasible. So in conclusion, so we propose a strategy for storing water vapor at high humidity levels for water production during the low humidity periods. And the feasibility is demonstrated by a techno-economic model. So the model shows that we can save a lot of money by adopting our strategy. So this work is supported by cost and is done in the lab led by Professor Norin Gaffo at KAUST. So this is our website, and we welcome like any type of collaborations. Okay, thank you for your listening. Thank you.
Thank you, Dr. G. So any question, if you have any question, you can write it in the chat or just simply raise your hand. We have one question in the chat. I apologize, but I missed a few minutes of the presentation and therefore I didn't fully understand how the water captured by the solution is recovered and how much energy is required for the process in relative relation to mass of water recovered.
Sorry, the first question is?
The first question is how the water captured by the solution is recovered and how much energy is required for the process in relation to the mass of water recovered?
I don't quite understand how the hygroscopic solution absorb water.
Yes, you can read it also in the chat.
Here?
Yes.
When the hygroscopic solution is heated like to its boiling point, the water vapor can evaporate from the hot feed and then condense on the coolant side. The condensate is the water we want to produce, a fresh water. Is the question you want to ask about this?
Oh no, you can just simply raise your hand. I will unmute you. Is it okay? Actually, she's asking about the energy. She wants to know how much energy needed.
It depends on the humidity levels. Like at high humidity, you spend less energy. At low humidity, you need more energy. But that exact number I cannot remember at this moment. Maybe I can share the data later.
And well, we have also one more question from Kumar. How LCOE calculated and what are the assumptions and what is the cost per liter of drinking water, including mineralization cost?
How is it calculated?
Yes.
LC? It's like an economic model. You have, of course, first the capital cost is what the prices you can find online or in the literatures. This is one part of the cost. The operational cost is calculated by a model we developed. This model is like a computational fluid dynamic model coupled with heat and mass transfer to simulate the atmospheric water harvesting system. In the model, we can get different parameters like flow rate, vapor flux, and different energy at the inlets or outlets. So these parameters can be applied to calculate the energy consumption. And yeah, this is the majority of the operational cost.
Thank you. Any other question? We have still 5 minutes for taking question. If there is no question, I can ask one. Yes, we have one in the chat. She mentioned, and I would also like some comments on the membrane. How is equipped constructed, and has the resistance of the membrane joint been tested?
The membrane, you mean the device here, presented here?
Yes.
Actually, we just published a paper about these devices. So it is constructed by 3D printing. We printed these channels, feed channels, hot channels, and then we assembled the channel with membranes like PTFE membrane with L-gap frames, which is also 3D printed, and then just seal it into an integrated device. So yeah, we have published one paper about this device.
Thank you. Any other question? We haven't seen some question.
Okay.
What is the purpose of the airstream in the absorption device section on slide 3?
To enhance the mass transfer, you know, we have a like convection mass transfer if you have a like airstream to accelerate this process.
Perfect. Thank you very much, Dr. T. I really appreciate. So we can start our next session. Let me introduce our next keynote speaker, Dr. Lucia Cattani. Dr. Cattani holds a PhD in technology for energy and environment and is the R&D manager at CISAS in Italy. She has been recognized as one of the Italian top 100 STEAM experts and received the 2024 Technovisionary International Award. Dr. Cattani is also a lecturer at the University of Pavia and served as a council member of the Lodi Order Engineer. The presentation title is Advanced Integrated Atmospheric Water Generators, Experiences and Future Developments. Thank you, Dr. Lucy. Can you start?
Yes, of course. Can you hear me?
Yes, very well.
I'm very honored to be here today and to speak about the Advanced Integrated Atmospheric Water. CS is a Switzerland company, I must underline. Okay, we know that the content of water in air is something meaningful, as already said, okay? So it is not a brand new idea to extract some water from air. We have the evidences of a myth of an ancient city of Greek dated to the 6th century before Christ, where all the water needed was covered by the dew collection. And Siebold in 1912 tried to prove such a theory and built a sort of on-air condenser. His experiment was not so successful. At any rate, the interest in atmospheric water has been awakened in the modern era. And in 1960, a first atmospheric water, a first sample of vapor compressor system in order to extract water from air was constructed, was built, and the experiment was successful. At any rate, the energy required was too much, so the idea was put aside for a while. But in the last 15 years, due to the technological evolution and to the worsening of the water crisis, atmospheric water has become more and more interesting. Thus, the atmospheric water is currently seen as a possible answer to the Blue Deal. Okay, but we must remember which are the main issues related to atmospheric water. First of all, we want to achieve significant quantities in relatively small place. We want tens, hundreds, thousands liters a day, okay? And we want to have affordable energy consumption and the system able to extract water in huge quantities of climates. And last but not least at all, we want high quality water, okay? We must remember that atmospheric water is not pollution free. Pollution can come from the process itself, can come from the device devoted in order to extract water from the water from air, and can come from the airborne. So we can have biological pollution, chemical pollution. So we must remember that atmospheric water harvesting is a multidisciplinary topic. Okay. One of the first ideas in order to extract significant quantities of water was to use directly air conditioning systems and to use directly the condensation, as we have already heard such a thing. Okay, but such a way is currently studied. Which are the main issues related to use directly an air condensation system in order to collect some water? First of all, the water quality. Some recent studies have addressed such a topic, but often various parameters are overlooked. Moreover, they can find inside, for example, heavy metals released by the coils, and it is hazardous. The other thing is the water quantity. Air conditioning systems are normally designed in order to minimize the latent heat, so to minimize the quantity of water that you can collect by them. So the next step, in order to use a vapor compressor reverse cycle to collect water, is to build a machine devoted to do that. Okay? So the atmospheric water generators based on a reverse cycle designed and built to do that. Which are the main problems related to such devices? The main problems are, first of all, the energy consumption, and secondly, the water quality sometimes is not okay because the issue is overlooked. So, which is the next step in order to achieve good yields, to achieve good quality, and to address the energy problem? It is the integrated AVG machines. Such a machine is built on the idea of the vapor compressor cycle, but it is a smart application because it is designed in order to offer the possibility to collect not only water, but also the by-side energy product of the cycle. You know that the process in order to collect water from air on a reverse cycle is to treat an external flux of air, which is cooled down under its dew point. Okay? Thus, you obtain a cooled and dried flux of air. Instead of dispose it into the environment, such an integrated machine makes available such a flux to the users in order to cool down some places, for example. The other thing you obtain is the water condensation, of course. And the third useful effect is the thermal energy coming from the air, okay? The coolant extracted some energy in order to cool down the air, and that energy is not disposed into the environment, but it is used as an heating source. Okay, thus with one energy coin, you obtain 3 useful effects. Thus, we can address the energy problem in such a way. Such a system can be combined to existing or new heating, ventilation, air conditioning systems in order to enhance their behavior. And on the other side is built from the beginning with a particular attention to the water quality. First, a strong air filtration system. Secondly, all the materials that come into contact with the condensate are at food grade. Third, the water treatment unit is tailored in order to achieve the wanted quality of the water. CS, the Swiss company, is specialized in such machines and was born 10 years ago and collaborates with the University of Pavia, currently, and developed some models of machine. Bigger model, which are able to produce thousands of liters a day while producing also cooling and heating, and medium-sized machine able to produce hundreds liters a day, and a small machine able to produce tens liters a day. After the construction of such a machine, one of the first issues was to understand how such a machine behaves in the various climates. So, a physically based real-time model integrated energy and mass conservation equations was built. Okay, thus we developed such model, and the model is able to give as output the machine behavior, including water production, energy consumption, cooling and heating power, when the input data are the temperature and relative humidity of the place. And we achieved a very, very interesting result because the error of our model fine-tuned on real machine is under the 5%. Such a model is very useful because it can be used not only to predict what a machine can do, but also to analyze real data in order to understand how a machine can behave in the future in place, for example. Now I'm going to describe to you one of our real experiences. We have a lot of case of study, of course, but I wanted to describe this one because it is interesting. We CS installed a machine in Dubai, in a worker village. It is an integrated machine, our 250, able to produce thousands of liters a day. Okay. The worker village is a village for workers, okay, and it is composed by several residential buildings, each one of them housing about 200 guests. The buildings needs heating, and there are common kitchens devoted to prepare meals that needs heating, cooling, and guests needs drinking water and domestic water. The domestic water is already produced by the desalinization system and can be heated up and used to make the shower, for example, while the drinking water is provided by means of bottles, okay, plastic bottles. We connect the machine to the common kitchens, and the dried and cooled air was delivered to the common kitchens, while the heating power of the machine was used to heat up the domestic water. Here you can see the tank of the domestic water and the existing LPG boiler that was used as a backup. And the drinking water was collected and then distributed by a dispenser in order to avoid the plastic. We carried out the test by 3 months. Data were analyzed by the University of Pavia, by me. And we calculated that it was possible to achieve the following results. The machine was able to cover all the heating needs of 2 residential buildings, in partially cover the needs, the cooling and heating needs of the common kitchen, and to provide drinking water for 800 persons a day. So it is a very impressive result. We made also an economic view, an economic assessment, and we found out that taking into account all the costs, materials, system installation, transport, and so on, and maintenance, and all the savings, electricity, LPG, water, the payback time of the investment was of only 2 years. After that, another study that we afforded was how to measure the efficiency of such multi-purpose machines, because these machines are multi-purpose. So we developed a particular index in order to be able to judge such kind of machine with one number. Not only machine able to produce water, heating, and cooling at the same time, but all the multi-purpose machine belonging to the heating, ventilation, and air conditioning systems. We developed an indicator before in order to assess the energy efficiency of water production, and then an integrated index in order to assess the efficiency of multipurpose machines. By means of one increasing number, we are able to make the judgment. But water quality. Atmospheric water is useful only for drinking purposes? Oh no, it can be used also for technical purposes. For example, we studied the quality of our machines and the quality of the water coming from machines, and we found out that it was okay in order to maintain photovoltaic panels, in order to be able to clean them directly with the water produced by the system. Enel Green Power asked us to install a machine in Ruby, which is a Mesa in Peru, and it has a very harsh conditions, a dry salt desert. Okay, the machine was particular because it was designed in order to produce in desertic conditions, and the water coming from it was used and is currently used to maintain the photovoltaic systems. But another application that it's very it is one of the last applications that we analyzed is about hydrogen generation. A request came from Japanese island in Ariomote, where it was planned to install a 2 megawatt photovoltaic field combined with electrolysis. And no fresh water was available because such an island is protected. It is a place where you cannot use fresh water for technical purposes. So we studied the quality of our machine, and we found out that without treatment, the water, because of all our attention to the materials composing the machine, to the air conditioning, to the air filtration system, and so was almost compatible with the chosen electrolyzer. So with a little treatment, we were able to achieve the wanted result, and thus we made a study about the possibility to integrate the machine with the electrolyzer and the photovoltaic system. We found out that only running the machine during the sunny hours, the machine was able to produce more than the requested water for the electrolyzer. So the rest, the exceeding quantity, was intended to clean up the panels, and the energy recovered by the maintenance, by the efficiency recovered by the maintenance, was enough to run the machine. So we closed the cycle, the energy cycle. It is interesting to analyze water from air as the raw material for hydrogen generation, because we can close a cycle. We extract water from air, we split it into hydrogen and oxygen. When the hydrogen then is recombined in order to obtain energy, we obtain also vapor, thus water in the air, and we close the cycle. On the basis of our results, the applied physics team of the University of Pavia, in collaboration with that of the University of Genoa, in 2023 won the PRIN funds for a 2-year-long project concerning the integration of such kind of machine with the heating, ventilation, air conditioning systems. The project wants to promote the water saving and the energy saving by means of the integration point of view. Okay, and now we are developing new applications, and we are developing further studies about this integration. First of all, we are studying the dynamic behavior, both passive and active, of different buildings with complex structures, like an hospital, an industry, and so on. And we are also studying their existing plants, and we are studying what happens when we connect the existing plants with an integrated AWG, an air to water generator. We are studying how to interface real-time simulation tools, real-time energy simulation tools, with our tailored simulator tool in order to provide results in various climates and also to provide a tool for the designers. Okay. Another thing that we are studying is how to optimize the management of such a multi-purpose machine integrated with renewable resources and with energy storage systems with phase change materials. We are also studying the different climates of the world in order to understand which is the good frequency of data required in order to provide reliable results. Because, you know, if you have got a climate which is almost the same, you can use, for example, daily averages or monthly averages, and they are okay in order to make your simulation. But if you have got a climate which is very variable, the frequency must be thicker. Okay. And we are also studying how to improve our evaluating tool for water harvesting from air and for the multipurpose machines. Moreover, we are going to install a real machine, and our 25 machine able to produce hundreds of liters a day in the University of Pavia in order to conduct various experiments, not only on the water production, but also on the greenhouse climate control and water quality for technical purposes. We will go on electrolysis, but also on other studies about the use in hospitals, for example. And in CS, we are working on improving the efficiency of our machines with an in-depth study on the major items. We wanted to reduce the spaces, reduce the costs, improve the efficiency and the multi-purpose capabilities. So the functioning as a heat pump, the function is as a cooling system while producing water, always with the same energy consumption. Improving the control system in order to achieve even better results, and we wanted to expand the operational range. And we are also studying some hybrid solutions in order to encompass, for example, absorption materials to enlarge the operational range also in this case, and also to provide water extraction from air even in cold climates, which is the real main challenge. In conclusion, we can say that atmospheric water can be one of the means to address the water crisis and can be an alternative solution to the traditional ones. And the integrated approach can be a means that allow us to address not only the Blue Deal, but also the Green Deal at the same time, because we provide energy saving and water collecting from air with the same energy consumption at the same time, with the due quality, Besides the satisfactory results that we have already achieved, we are going on with our efforts to improve the techniques, to improve our judgment tools, to improve our simulation tools, and so on, in order to make atmospheric water something that is a very real sustainable source of water. Thank you for your kind attention.
Thank you very much, Dr. Lucia. Interesting pilot system. So is there any question? If there is any question, just simply raise your hand or you can write in chat. We have one question from Daniel. Where can we read more from details from the device like efficiency and components?
Okay, can you hear me? Yes. Okay, we published various papers about our machine, and you can find the link in the presentation. But if you wanted to know something more, you can contact directly CS, and we will be able to give to you all the particular about our machine, includes how it can behave in the Arizona desert, for example, because as I said you before, we developed such a model that let us to understand the behavior of the machine. Moreover, we have got a net of 10,000 of climatic stations. Okay, they are not ours, of course. We take data from them in order to understand how our machine behave in one zone, another zone, and so on. So we can provide all the data you want if you contact the CS. It's difficult in cold climates. Can't we use condenser heat to design water? I'm reading a question in the chat box. May I?
Yes, of course.
Atmospheric water harvesting is difficult in cold climates. Yes, it is. It is not simple because, as you know, we can imagine air as a sponge. If temperature is high, the sponge is large. If the temperature is low, the sponge is little. So even if you have got relative humidity at 10% and the sponge is little, even if you are able to squeeze the sponge, all the sponge, you can harvest only few drops of water. This is the first thing. So it is more challenging to extract water in cold places. So can't we use condenser heat to design water harvester for such climate? Condenser heat. I can't understand condenser heat. We can use something that absorb water in such climates. It is better. But you must remember that we cannot collect very significant quantities of water if there is not water in the air. This must be remembered. And in cold climates, you have very, very low quantity of water generally in the air. So it is very challenging from this point of view. Thank you. Okay.
Okay, we can take one question from Alisha. You are on mute right now. Alisha? Zain Alisha.
Okay, thank you. I can't.
You are on mute right now. Right now you are on mute. Just simply open your mic. If there is any issue, you can write your question also here. Perfect. He's writing, Dr. Lucy. So I can also have one question. How does the integration of advanced atmospheric water generator with existing HVAC system impact the overall energy efficiency?
Excuse me, can you repeat? Because I was reading one question on the chat.
Okay, no problem. How does the integration of advanced atmospheric water generator with existing HVAC system impact the overall energy efficiency, and what are the specific improvement in water production rate?
Okay, as you know, we are watching a system that is able to provide more than one. The process itself of water extracting from air will give to you the two said by-side products. Okay, so the efficiency of the machine is more or less the same if you are able to produce a machine with a right control system. Okay, you must be able to make a very, very smart control system to provide heating and cooling and so on. So if we take a look to the overall efficiency of the machine when producing water and at the same time giving cooling and heating, of course you must choose what you want to obtain. If you want to obtain water, the machine is optimized in order to consume the less energy possible to produce the water. At the same time, you will obtain some cooling and some heating. Maybe the heating will be not enough and the cooling will be not enough for your purposes, but it's not a problem because the machine is something that you can integrate with the existing plants. So it can give you the largest part of the heating and cooling requests, and what is lacking can be afforded by the backup system. Okay, so the overall consumption of the system, of the integrated system, is less of a traditional system composed by three things, making each one of them only one useful effect. I hope I answered your question.
Yes, sure. We have one question in chat from Zain Ali Shah. Do you have any performance evaluation frameworks like humidity harvesting index on which we can judge the efficiency of a machine?
Yes, of course, we have an indicator that we studied for the purpose. So we have got an indicator that is able to say to you how much water you obtain, and it is the ratio between the obtained water and the energy consumption of the whole machine, okay? And the water is transformed into energy, okay? So it has the same perspective of the COP and EER. And we have got also the integrated index that allow users to understand the overall, we can say, efficiency of the multi-purpose machine and different machines. So we of course evaluated our machine also with other index and with other indicators, such as, for example, the SEC, the specific energy consumption. And of course, we carried out some judgment among different machines. We can provide results, of course, and in our papers you can find out the results of our assessment.
Perfect. Any other question? We still have around 5 minutes to take questions. Any question?
There is a question in the chat. I saw that we didn't.
I missed it.
May I read it?
Yes, of course.
What do you think about integrated solvent-based water harvesting, like using desiccant, etc.? Okay, this is one of our dreams, I might say so. We are studying it, but we must remember, first of all, we want the water quality. So we must be sure that no desiccant will put inside our harvested water something harmful. So this is the first point that we want to be sure to assure, okay, to the user. Secondly, we are studying how integrate our machine with a system able to absorb the water when the outside conditions are harsh. As I said you before, in cold climates could be a good idea. There are already laboratory scale hybrid systems, and we are studying our own solution in order to achieve the best results based on a vapor compressor system, but also mixed up with absorbent materials. You must remember that in the end, you have always to condensate the humidity. Sorption and desorption, there are some gels that are able to hydrogel that are able to convert the humidity in some drops of liquid water, but only a few parts. Normally, what you obtain by desiccants is to absorb the water and then desorb it as vapor. So you enhance the dew point. In the end, you must condensate it. So yes, integrate the two systems is a good idea, but it must be carried out in a smart way. And we are studying it.
Okay, we have still one more question, huh?
as you know, fog nets. Ok, ce n'è un altro.
Yes, please go ahead.
Okay. As you know, fog nets might be a cost-effective harvester for humid and foggy area. Yes, foggy. For example, in my city, that is very foggy, but we have also a lot of water. How do you see them as a commercial device? I am asking this because your company focused on different methods of art, but not. We did not focus on fog nets because, as you said, it is only for particular places. So for such particular places, of course, there are a lot of studies on shapes, materials, methods, and so on, enhancing the fog net capability to collect water. But mind the water quality, because fog nets do not filter air. Fog nets do not avoid insects to go inside the water and so on. So they can be, of course, something cost effective, but which is the quality of what you harvested? Thank you.
Okay, any other question? We have one more speaker for this session, detailed session. Before starting this session, I would like to ask one small question. You can answer, anyone can answer in the chat. We have several terms to call atmospheric water harvesting, such as atmospheric water harvesting, atmospheric water capturing, atmospheric water extraction, and so on. Which one do you prefer? I asked you before this question previously.
I know, but I use capturing because you said me that you were all that you decided to use capturing. So in my last paper, I'm writing capture.
But anyone can answer. Which one do you prefer? Atmospheric water harvesting, atmospheric water capturing, or atmospheric water extraction? We try to, find a perfect name for it. Okay, atmospheric water generator, atmospheric water harvesting, atmospheric water extraction, atmospheric water harvesting, atmospheric water generator, atmospheric water harvesting and extraction.
But the generator is the device.
Yes, I agree with you. Atmospheric water harvester, atmospheric water harvesting, extraction. Anyone else would like to share his idea with us? Atmospheric water extraction, harvesting. People mostly like atmospheric water harvesting and atmospheric water drain. Yes, Frank, let me unmute you. Yes, Frank, you can just simply open your mic. You're on mute.
There we go. Can you hear me now?
Yes, perfect.
Fabulous. WAHA prefers the term atmospheric water extraction because we utilize solid sorbent materials, which technically function as an extractor of H2O molecules from the air, singularly capturing only H2O molecules, and therefore the separation of those molecules makes it a perfect separator, unlike condensation systems, mechanical vapor compression systems, which capture whatever happens to be in the air.
Perfect reason. Hunter King mentioned, why not separation? Anyone to reply? Because actually we try to find it, a good term. Harvesting, extraction, separation. We have a lot of comments right now in the chat. Kumar mentioned generator is good, but it looks like extensive to carbon use, like a diesel generator. Harvesting sounds like it's sustainable. So let me introduce Dr. Marcia Silva. Dr. Silva earned her PhD in chemical and biological engineering from the Faculty of Engineering at the University of Porto, with a thesis titled Water Harvesting by Absorption-Based Process on MOF. She is a senior researcher, and her work focuses on absorption-based process using environmental-friendly nanomaterial. Presentation title: Revolutionizing Water Supply, Atmospheric Water Harvesting, and Vapor Capture with MOFs. Dr. Marcia, may you please share your screen? Dr. Marcia? Can you hear me? Dr. Marcia Silva?
Hi. Hi,
yes,
everyone.
we can hear you right now.
Okay. Can I share my presentation?
Yes, of course.
Okay, thank you. Okay, can you see?
Yes, perfect.
Okay, thank you. And so, good afternoon to everyone. My name is Marcia Patricia Cardoso Silva from Portugal. I will present some of my PhD results obtained. I will show some results from my PhD that I have 3 years ago. So, this session will cover the following topics: introduction to water scarcity and its global impact. I will do an overview of atmospheric water harvesting technologies. I will show also the role of MOFs in water vapor capture. And I will show some of my results, the process development, the main conclusions, and some of the future work that I propose, and it is being implemented. So, water scarcity occurs when water demand exceeds the available supply, a condition that affects billions of people worldwide. Factors such as population growth, climate change, and population exacerbates this issue, leading to severe social, economic, and environment challenges. The figure beside shows the forecast of water stress to the next year. Here we have the Iberian Peninsula, that it's composed by Spain and also Portugal. And we can see that there is a predicted increasing trend of stress, with the southern region being the most affected along the years. Okay. So, traditional water sources are heavily dependent on predictable rainfall patterns and infrastructure, which are increasingly reliable due to climate change. Water scarcity is a problem, especially in arid and semi-arid regions. Extracting water from there could be a solution, as it can be applied in areas where there is no availability of liquid water. So, there is 10 times more water in the air compared to the total amount of surface water in rivers and lakes. There are 3 main types of atmospheric water harvesting technologies. Type 1, heat pumps or radiative cooling. Type 2, water vapor concentration by desiccant. Type 3, convection-induced control in a structure. During my PhD, I studied the type 2, the water vapor concentration by desiccants. Absorption-based process should use materials that require low energy regeneration, step shifts the isotherms, water stability and high cycling performance, and a high water capacity. The most common desiccants are zeolites, alumina, another ones are carbon active, so on. However, they are not ideal materials for water capture, such as zeolites have a favorable water absorption isotherm, but the material's regeneration is more complicated and requires high temperature. MOFs belong to a new class of desiccant materials and are promising for water absorption. One of the major advantages of MOF is the wide variety of isotherms that they offer. Here we can see a lot of examples of materials of novel water desiccants with different typologies of isotherms. The MOFs are crystalline hybrid materials known for their high surface area and tunable porosity, make them ideal for a variety of applications such as hydrogen storage, catalysis, heat pumps, and absorption and inspiration. So, during my PhD, I tried to solve this problem, the water scarcity, especially in arid and semi-arid areas that can be mitigated through atmospheric water capture. To this end, an absorptive process capable of producing water was developed. Was the objective of my PhD, design an efficient absorptive process for water harvesting. So, these were the materials selected to absorb were 5 MOFs, aluminium fume, calcine, 1160 aluminium, 1100 iron, 1125 titanium mina. These 3 have the same metal, the aluminium. All the materials were provided by CRIT, the Korea Research Institute of Chemical Technology. The materials were characterized using various classical techniques, such as XRD, helium picnometry, particles range, something like that techniques. So, this is the gravimetric method. These isotherms were determined using the gravimetric method with a ribotherm, magnetic suspension balance, that is here. The gas was introduced into the bands at different pressures, and the temperature was controlled by circulating fluid around the balance. The isotherms of O2, N2, CO2, and water vapor were measured between 283 and 343 Kelvin. Prior to isotherms measurements, the absorbent was activated at 123 Kelvin under vacuum for 12 hours. To do the absorption dynamic study, breakthrough curves were performed in a fixed bed at 1 bar and the ambient temperature. The column was regenerated with helium and fed by 2 gas streams, here and here. One of these streams is presaturated by passing through a bubbler. Then temperature and humidity sensors are placed at the inlet and outlet of the column, along with a temperature sensor in the middle of the column. The gas mixture at the column exit is analyzed by an infrared analyzer. Okay, these are the conditions of the operation. Here, in the drift analysis, the effects of temperature, water absorption, CO2 absorption, and co-absorption of CO2 and water vapor were evaluated. All spectra were measured at ambient temperature and the pressure of 1 bar. The thermogravimetric analysis of materials demonstrated that MOFs showed stability at high temperatures, like you can see in this graph. All of them have demonstrated great stability until the temperatures until 500 degrees. Then two isotherms of the MOFs, except for μ100 iron, exhibit type 1 characteristic, typical of microporous materials. In μ100 iron, the isotherm is of both type 1 and type 4, indicated the presence of micro and mesoporous cavities. As material indeed possesses two types of cavities, the material has the highest pore volume. Regarding to CO2 absorption, all materials exhibit type 1 isotherms. The equilibrium absorption isotherms for O2 and N2 are linear for all of them. Meanwhile, CO2 exhibits type 1 isotherms. The amount absorbed for O2 and N2 ranges from 0 to 1.6 mol per kilograms. For CO2, it ranges from 0 to 8 mol per kilogram, indicating that all materials show a higher affinity for CO2. The isotherms were fitted using the Langmuir model, and the equilibrium constant was determined using the Van 't Hoff equations. The water absorption equilibrium isotherms for all fumarate are of type 4, where a small amount of water vapor is absorbed at low pressures. You can see a little bump here. As the pressures increase, the materials exhibit hydrophilic behavior, showing an increase in absorption. The cooperative multimolecular model absorption is this one, was applied to fit the isotherms. This model consists of an Ising model component and the Langmuir model. An initial fit was made, but since it could not accurately predict the results in fixed bed, a new fit was made to better describe the dynamic model. So I present here the two fittings. Here, the same fitting was applied to the water vapor absorption equilibrium isotherms, but now for Cattani. These isotherms are also of type 4. And here I show the main results obtained by fitting the model to the isotherm. For μ160 aluminium, the isotherms are 5 and were also fitted with the semi-MES model. I present here the main results. In the μ100 iron exists isotherms type 6, showing different plateaus, like you can see here, and here another plateau. And these plateaus are due to the filling of the two types of cavities, as evidenced by the N2 absorption isotherms. The isotherms are fitted using a new model, a dual Ising single Langmuir model, that are composed by Ising and a Langmuir model. Finally, for μ125 titanium amine, the water vapor absorption equilibrium isotherms are of type 4 and are also fitted using the semi-MES model. You can see here that it was very well fitted by this model. So the obtained data allows for the development of a mathematical model aimed to describe the dynamic behavior of water absorption. This model was then validated using the experimental data obtained from the breakthrough curves and was later used as an essential tool for developing the cycle water capture process. So with the mathematical model and the validations, we had the absorption dynamic behavior. Here, the water breakthrough curve for 160 aluminum is presented in this figure. During absorption, this perceived front is observed up to 5% of relative humidity, which corresponds to an favorable isotherm up to 5% in the equilibrium data. Subsequently, a compressive front is observed, and during the absorption stage, a dispersive front is observed up to 40% of relative humidity, followed by a compressive front. The behavior is consistent with the equilibrium data, as from 50 to 14%, the isotherm is unfavorable, and then it becomes favorable, like you can see here, okay, and here. For these three materials, they also follow the expected behavior based on the equilibrium data. The dynamic absorption behavior of water was well predicted by the mathematical model, particularly in 125 titanium amina. You can see here that there is almost no deviation between the model and the experimental data. On the other hand, both findings apply to the water water vapor absorption equilibrium isotherm for alpha-marat failed to describe its dynamic behavior. You can see here that they are all both are very far from the experimental data points. So, sorry. In the water saturation curves with N2 and CO2, it was observed that these gases do not influence the dynamic behavior of water absorption. And in the model, although a multiple component equilibrium is not considered, it is able to predict the breakthrough curve well. In the drift experiments show that water band decrease with the increasing of temperature, like it's supposed, and the structure is not affected up to temperatures above up to temperatures of 123 Kelvin. Water absorption increased the water band, and a similar behavior is observed during the absorption with CO2. As you can see here, with along with the increase of the material with the gases, there we can see here that the band of water is increasing. Okay, here we only have CO2, so we can see the band of water increasing like it's supposed. So, two processes were considered for water production: a TSA and a PTSA. In PSA, an operating pressure of 0.3 bar was considered. And for both processes, two stages were considered: feeding at night and concurrent purge during the day. The optimal absorption and absorption times were obtained by trial and error. The following environmental conditions were considered: a temperature of 298 degrees, relative humidity of 50 degrees, and a pressure about 1 bar. So, different purge and condensation temperatures here were used. In brands 5 and 8, ambient temperature was considered as the temperature of condensation, and at 353 and 373 degrees were considered as purge temperatures. In the remembrance, condensation temperatures of 283 Kelvin and 288 Kelvin were used, and purge temperatures of 1335, 30, and 53 and 373 degrees. The goal of PTSCA is this one process. Was to lower the purge temperature. However, it resulted in a decreased productivity compared to the TSA. Okay. Sorry. Another idea was to redirect the dry air from the column outlet back during the feeding to be used later in purge. However, did not impact productivity compared to the runtime, have the same productivity. They didn't affect the process. So, for this scenario, the internal relative humidity and temperature history of the gas at the middle and was achieved in the run 6 with the highest temperature of purge and the lowest temperature of condensation. Then I will indicate for this scenario the internal relative humidity and the temperature history of the gas at the middle and at the end of the column as well. The relative humidity profile shows that by the end of the absorption stage, the column was fully regenerated. Okay. The internal relative humidity profile indicates that at 5,000 seconds before the end of the absorption, the shock wave reaches the end of the column, and 5,000 seconds before the end of the absorption, the column is nearly saturated, reaching the maximum absorption capacity, that's about 18 mole per kilogram. Here, the TSCA process served as a baseline study, now with Cattani, 1100 iron and 1160 aluminium. The operation conditions were maintained and condensation temperature was set to 183 Kelvin. For the column volume of 0.98 meter per square meter, it was found that the cycle will need to be longer than 1 day to be completed. So a column with one third of the initial volume was tested, achieving a maximum of 81.3 liters per day. The same issue occurred with the 1100 iron, and the same adjustment was made, achieving a productivity of about 87 liters per day. Cycle times were optimized using the particle swarm optimization model. In this model, the particle tries to reach its best position relative to the group by adjusting its velocity. So the times were optimized by these models. So the purge was set at 353 Kelvin and the flow rate was variated. As expected, the highest productivity was achieved at the highest flow rate. Next, the flow rate was fixed and the purge temperature was varied. The highest productivity was achieved at the highest temperatures. With main conclusions, the thermal stability of Cattani is thermal stable until 1,100 the Kelvin. But most of MOFs are stable at 630 Kelvin. In adsorption equilibrium, we saw what the most material is suitable for each region. For example, for regions with low relative humidity, the 1160 aluminium is more suitable. And Cattani and 1125 titanium aluminium are suitable for regions with relative humidity of 20 degrees. Our aluminium fumarate displays a sharp uptake for relative pressures between 25% and 40%. And the 100 iron that have two types of cavity are suitable for two types of regions, one for relative humidity between 20 and 30%, and the other one between 35 to 40%. To the dynamic behavior, we can see that the model developed was able to predict accepting for aluminum fumarate adsorption. Water adsorption does not affect water adsorption behavior. And the drift analysis shows that the structure is stable after several cycles, even exposed at different temperatures. So these are the main conclusions for each kind of MOF, and the design of an efficient adsorption process for water harvesting was achieved. The model is flexible and able to predict the process performance for different regions, absorption, absorbance, and operating conditions. These are the main the important operating conditions that we achieved these results. The future work will focus on enhancing the stability and regeneration efficiency of MOFs, as well as integrating these materials into a scalable atmospheric water harvesting system. Another adsorption are being testing, and we are thinking to apply a mineralization process to obtain potable water to drink. We need also to check the drink safety, mainly because of the pollutants, and try a strategy to avoid anti-foaming in the material. So, in summary, MOFs offer a promising solution to water scarcity by enabling efficient atmospheric water harvesting in a range of environmental conditions. And by continuing to refine these materials and process, we can make significant strides toward sustainable water supply solutions. So, thank you all for your attention.